Okay, good morning, everyone. I want to welcome you to another statistical learning class. Of course, today we're going to be focusing on uh, another two classes of regression that we call the principal component regression and the partial least squared regression. Now, before now, I think I actually walk you through different types of regression that we have in statistical learning. Of course, before go ahead, starting this topic, I think I'm gonna have a recap. It's good to always have a recap so that we can retrace our step back to this particular topic. So, the idea started by trying to characterize relationship between variables, one response and maybe several predators. And of course, we started by way of model specification. We specify our model, and after specifying our model, we conducted what I called what I call a preliminary investigation, trying to have the idea of the relationship, by constructing the scatter plots, and after that, um, you have a model parameter estimation. You use the method of least squared, and of course, before you can use the method of least squared approach to estimate regression parameters, you four of us need to investigate. You know, when you specify the model, we have assumptions that revolve around the error time. And of course, after you are done estimating the parameters in the model, the next is to perform what I call regression diagnostics. The regression diagnostics uh, is necessary to investigate whether assumptions of linearity or assumptions of constant variance, assumptions of normality, absence of multicollinearity, absence of outlier and high leverage. And of course, I think I've walked you through how to investigate all of that. But let me tell you this, the major issue that we have, okay, is what I call that we've been trying to address is what I call multicollinearity. Multicollinearity is a situation in modeling where predictor variables correlate. We don't want that kind of situation. When the predictor variable correlates, it will make what I call regression coefficient unstable. And when regression coefficient become unstable, what is going to happen? They even though they will be unbiased, but they can no longer be consistent. The moment they are no longer consistent, then I'm actually going to say there's going to be issue with statistical inference, whether you want to test hypothesis, the what you're going to get, the decision you're going to take will not be reliable, or you construct a confidence interval because when this problem occur, it will inflate the variance of the regression parameter. And when it inflates the variance of regression parameter, the standard error will also be inflated because the standard error is the square root of the variance of regression parameter. Now, the moment there's multicollinearity, then it means you cannot use the least square to estimate the parameter in the regression model. And that was the reason why we are seeking a very vibrant, more robust approach that can be used to deal with multicollinearity. Now, I remember one of the approach that we use, one of the techniques that we use in removing and dealing with multicollinearity, we started with all subset selection. Okay, now I'm going to tell you this. All subset selection does not fix multicollinearity, and all subset selection may not necessarily remove multicollinearity. The all subset selection will consider all possible models, okay, from simple to complicated, okay, using metric of evaluation, AIC, BIC, and R square, and so on like that. Okay, now after that, we consider regularization technique, the regularization technique, lasso and the ridge. Now, let me tell you this. Lasso and the ridge, the two of them perform excellently, compared to, uh, the off subset selection. In fact, before I walk you through um, regularization technique, I think after off subset selection, we also consider stepwise regression, forward selection, and backward elimination. Now, let me tell you this: the forward and the backward elimination iteratively add and remove variable. Okay, and let me tell you this: that very approach, okay, there's possibility is going to help to remove a pair of variable that is collinear, but stepwise regression does not fix multicollinearity problem. Now, we have two models that we use that may not be able to adequately fix multicollinearity problem. The first one, or subset selection. The second one, the stepwise regression. Now the story continues. The search for model to deal with multicollinearity continue. Then we now find ourselves in what I call regularization. The regularization like lasso and ridge. Let me tell you, the two of them perform great, compare to the off subset selection and the stepwise regression. Now, after I'm done with these two, you know what I'm going to do? I will rank all of them based on effectiveness, and you're actually going to see the best and the least. But before I, rank that, I want to introduce you to another regression type alternative that can be used to address multicollinearity. Now, this very two, they based their principle on principal component analysis. And that was the reason why on Wednesday, I introduced you to principal component analysis. So the idea of principal component analysis is being used by these two type of regression. Now, I want to welcome you to principal. I'll first talk about principal component regression. And after that, then I'm going to talk about partial least square regression. You're going to see you're going to see the kind of difference or the connection between the two. Then finally, then I will now rank all the intervention in terms of regression type to deal with multicollinearity. Now, let's get started. Principal component regression. Now, let me tell you this. If I want to apply simple component regression, I will need to first convert, okay, the predictor variables into uncorrelated variable. How? We're actually going to use the approach that we use on Wednesday, okay, using principal component analysis. So using principal component analysis, we will need to first transform the predators. Okay, we're going to transform the predators. Okay, after transforming the predators, and that is what you're actually seeing here. But don't forget, before transforming the predator, we need to first standardize, because there's possibility some predator may have, we may be on the higher scale than the others. We need to first bring them to uniform scale, the same scale, so that one variable does not dominate the other. So after the standardization, then we run the PCA. Okay, when we run the PCA, we actually are going to end up with a principal component 1 up to principal component m. Don't forget, the number of principal component should be less than the number of predators. And at the end of the day, using certain selection criteria in the principal component analysis to choose the number of principal components, okay, then finally, we are now going to perform regression. Okay, we're going to perform regression using the principal component as the new predators. Okay, you can see that that's going to be the model now. Does that make sense? Okay, so to choose a particular number of principal of model that work, the idea of a cross validation can actually be brought into play, where you train the model first, then you test the performance of the model, okay, using the criteria of a mean-square error or a root mean-square error. Then you compare, because you want to be able to see, what is the combination of the principal components am I going to have in my model. I'm going to tell you the weakness of this model, of this principal component regression, okay? And I'm going to tell you the strength. The strength of the principal component regression. This actually eliminates multicollinearity. I'm going to say that again. Principal component regression eliminates multicollinearity because the predator variable used have been transformed. The original predator variables have been transformed. And don't forget, each principal component is still a linear combination of the old features. Because of that, even though the principal component analysis, even though the principal component regression has succeeded in eliminating multicollinearity, but you know what? It's going to, lead us into interpretation issue. I'm going to say that again, because transformation of the original predators is involved, then this will lead to problem of interpretation. It solves a problem, but it creates another problem. Is there any question with principal component regression? And you know why that happened? That happened because in the principal component regression, when you are selecting the principal components into this regression model, you only seek variance maximization of the predator variables only. I'm going to say that again. Selecting your principal components to be used as a predator in the regression model, the way you select the principal component, you focus on maximizing the variance in the original in the original predator only. You did not consider their relationship with the response when you were selecting your principal components. And that is the reason why there's going to be this principal component regression, even though is fantastic, it was able to eliminate multicollinearity, but it's going to have a very low predictive accuracy. Very low predictive accuracy because you only maximize variance around predator, leading to you obtaining the principal components. Does that make sense? Okay. Now, how can we improve on the principal component regression? The way to improve on the principal component regression, can we have a way to maximize, okay, not only variance in the predator, but to maximize the covariance between predator and the response? Covariance maximization will solve the problem. The principal component regression ignore, okay, the response variable. It ignore the connection between the predator and the response variable when figuring out the principal component. Does that make sense? Okay, so, and that is why we're going to be seeking, okay, that's why we're actually going to be seeking partial least squared regression. Now, let me tell you the difference between principal component regression and partial least squared regression. The two of them make use of principal components. I'm going to say that again. The similarity between partial least square regression and the principal component regression, the two of them make use of principal component, but the way the principal components are constructed is not the same. In the principal component regression, the way the principal components were constructed, they only maximize the variance in the predators only. But in the partial least square, okay, they maximize the covariance between predators and the response to be able to derive the principal components. Does that make sense? Okay. Now, whether in the principal component regression or in the partial least squared, we normally use it. You can use a cross validation to be able to know how many principal components do I need in my regression model. Do I need one? Do I need two? Up to, do I need all of them? Okay, that is when we're going to compute a mean square error, but the mean square error we're talking about is going to be a mean square error for the test because you're going to split your data. Does that make sense? Okay, and I said something here. Okay, uh, whether you are, whether you are running PCA is the principal component regression. Okay, or you are running PCA, principal component analysis. Okay, make sure you standardize your variable, okay, before you can actually use that. Okay, and of course, there's so many criteria that can be used to arrive at the best model at the end of the day. You can use a cross validation. You can also use the proportion of total variance explained. What do you want to arrive at? You want to arrive at the number of principal components that work, or you can use the AIC, the BIC, and the R square adjusted. Okay, but you know what I want to do now? I want to show you a code. How do I run principal component regression in R? Take a look at that. If you want to do a principal component regression or want to do whatever, you need to set a seed for reproducibility. And you need to load a package called PLS. Okay, I need you to pay attention. I want to use a data set in R, okay, and that the data set has a response variable horsepower, with MPG, mile per gallon, and displacement and so on like that. I need you to pay attention now. Take a look at this. Okay, what do you see here? That's a PCR, right? Can you see PCR? That's principal component regression. You're actually asking R to run a principal component regression. Okay, and look at the scale. Scale equal to true, right? That means standardize. You're asking the how to standardize. Don't forget that. Okay, then you actually specify Take a look at this. You're doing a cross validation, okay? Because you need cross validation to be able to know the number of principal components that work, okay? Then you do the model summary. Then not only that, you can visualize your model based on mean square error for prediction, based on R squared, okay? And after that, after you are done selecting the best model, go ahead and make a prediction, okay? You know, we define your data set into training and testing if you want to make prediction, okay? So making prediction, take a look at the code, and finally, you're actually going to compute the root mean square error. Now, some of you may be wondering, what is the difference between mean square error and the root mean square error? They are actually measuring the same thing. It's going to be the same difference between variance and standard deviation. Okay, so variance does not have the same units as the mean because variance is a square unit, right? If I wanted to have the same unit as the mean, I find the square root of variance. That gives me standard deviation, right? And that's why we. So also here, the mean square error, okay, is something squared. Is the square of the distance between the what your model predicts and the origin, what is in the test data. So I can take the square root of that too. Okay, so here I'm using a root mean square error. Now, when I use the result that I have in the root mean square error was 56.8. If you run this code for the data set, is in R 86549. That was the mean square error that I got. Okay, 56 point something. Okay, now that is for the principal component regression. Now I also want to, for the partial least square regression, don't forget, I told you the other time, we seek a maximization of the covariance between the predictor and the response for us to be able to construct the principal components. Okay, now this is the step. You standardize, but in the partial least square, in the principal component regression, you only standardize predictor. But in the partial least square, you are standardizing both response and predictor because you want to construct your principal component, maximizing variation, covariation between the response and predictor. And that is why the two variables need to be standardized. Okay? And after that, you construct, you obtain the PLS. And after obtaining, I said, use the method of least square to fit a linear regression using the PLS component as predictor. The PLS component that you have constructed, putting into consideration, maximizing predictor or the covariance between predictor and the response. Then you use a k-fold cross-validation to find the optimal PLS component to keep in the model. If you don't want to use a k-fold, you can also use the percentage of variance explained by the principal component. You can also use so that is that. Now, I want to show you the step in R for partial least squared. For the same data, the other time I got 56 point something as the root mean square error for principal component regression. I also want to use partial least square, okay, for the same data set. I'm also going to load PLS. After that, after loading, okay, if you take a look at this now, okay, I need you to pay attention to this. What is this? Do you see that? The other time, it was PCR. What do you see now? PLSR, partial least square regression. Okay? You're still looking at the relationship between that. The data is empty chaos, is in R. And you scale equal to true. If you choose scale equal to false, you are not standardizing your data. That's not good. Then cross validation. Okay. Now you see the difference in the two. Okay. You do not need to worry too much because the code is R input, just PLSR. The other one is PCR. Okay. But at the end, after that, you choose the number of PLS. Okay. If you take a look at what I have here, please pay attention. I'm showing a result that come out using the partial least square regression. Please pay attention. Now, I've conducted cross-validation using 10 random segment, and this is without any principal components. Of course, without any principal component, it's going to be intercept. The root mean square error for prediction was 69.66. Do you see that? With only one principal component, the error goes down to this, right? The root mean square error goes down to that. That is with one principal component. With two principal components, the error goes down to 35.48. When you make an attempt to go for three principal components, what has happened? The error goes up. So based on the cross-validation now, two principal components is optimal. Does that make sense? Who doesn't understand that? I'm explaining the result that came out of the partial least square regression. Okay, so right now, the optimal number of principal components should be two. Because if you go beyond two principal components, you're actually going to have the root mean square error prediction increased. If you want to go by another approach, if you don't want to use if you don't want to use a cross validation, if you want to use the conventional percentage variance explained in principal component analysis, okay, take a look at this. I need you to pay attention. Okay, if you take a look at this, right? If you continue, that is for the one, okay? We normally want the one that have the highest percentage variance explained. Okay, now when you take a look at what I have now, okay, with one principal component, okay, if you with two principal components, with three principal components, with all the principal component, we all know is going to be 100%. Based on the percentage explained, we can actually have a kind of a threshold. Okay. If you want to go by 80% threshold, I'm still going to select two principal components. With 80% threshold. Okay. I needed to pay attention to that. Okay. Now, if you take a look at what I have, I needed to pay attention now. Okay. When I continue, when I goes into prediction, when I want to use the model to make a prediction, I got this as a root mean square error. But when I use a principal component regression, it was 56 point something. But with a partial least square, the root mean square error is 54.89, which is a reduction in root mean square error. Okay, when the root mean square error is smaller, okay, that indicates high predictive power. Does that make sense? Now, I've walked you through all of that. Give me 1 second. What do I have? Okay, I think I have nothing more. Now, you know what I want to do now? What I actually want to do is this. Least squared, please pay attention. Least squared or subsets. I'm actually going to say AS or subset. Stepwise regression. Okay. Lasso. Okay. Lasso. Okay. I want to rank them now. Please pay attention. Lasso, ridge, ridge. Okay. Ridge regression. P PCR, principal component regression. P partial least square regression. How many models do I have on the board? I have 7 models. I want to rank them when multicollinearity is present. Are you ready? Okay. You know, when multicollinearity is present in data set, I said something the other time. Okay, the regression coefficient will be unstable. Okay, even though they are still going to be unbiased, but they are never going to be consistent anymore. And when estimator has issue with consistency, it will affect statistical inference. Now, you cannot use least square. There's going to be an issue. You're going to mislead. Least square approach is out completely. Now, if the least square approach is out completely, using least square approach is going to mislead. The next alternative approach that we're going to consider in dealing with multicollinearity is of subset selection approach. Now, the of subset selection approach involve conducting different form of possible subset models. But let me tell you this, that approach may not be able to remove multicollinearity and may not even adjust, and do effect the created a multicollinearity. But all subset selection is better than the least square. Does that make sense? All subset selection is better than the least square. Does that make sense? Now, the all subset selection, despite the fact that, we know that in addition to not able to remove and, fix multicollinearity problem, it is not also economic friendly in terms of application for large data set. When you have large data set, don't forget, you're actually feeding, let's say for instance, you have high-dimensional data where there's so many explanatory variables, then you're actually going to consider so many models before you arrive at the best. Now, the next on the line, okay, stepwise regression. When I talk about stepwise regression, I'm actually talking about the forward selection and the backward elimination. Of course, what stepwise regression does is to iteratively remove or add variable into the model using p-value, AIC, BIC, and so on like that. Let me tell you this, there's possibility stepwise regression who eliminates one of the pairs of correlated variable, but cannot fix the problem, the effect created by multicollinearity. Let me tell you this. Police arrested this guy. Police arrested this guy. right? But this guy has already caused a damage. Maybe this guy commit a criminal, as a criminal offense, okay, and he has committed a damage in the community. Arresting this guy, which means police has removed, which means this stepwise regression has removed multicollinearity, but does it really solve? Because the multicollinearity has already left an effect. Does that make sense? The only thing that's going to happen is when somebody commits an offense and police arrest the person, it's only going to serve as a relief to that community. Then they're not likely going to have 100% relief because the damage has already been done. So what I'm trying to talk about with a stepwise regression, even though if there's possibility, the stepwise regression will remove one of the variable causing the problem, but may not necessarily address the effect created by that particular variable. Okay. Now, if I'm going to start ranking them, okay, like I said, the least square is a no-go area when multicollinearity exists. The all subset selection is good in terms of effectiveness in dealing with multicollinearity is poor. I'm actually going to rank that poor to moderate, poor to moderate. Okay, I'm actually going to rank that poor to moderate. Now, then for the stepwise regression, I'm going to rank, stepwise regression, probably moderate to good, moderate to good. Okay, moderate to good. But take a look at this four. Oh my God, we want to look at this four now. Lasso, reach, principal component regression, okay, and the PLSR. If I'm going to, these four, they can compete favorably in dealing with multicollinearity, but I'm going to tell you, I'm going to start from the list. I've eliminated this guy, right? Because their performance from poor to maybe medium. But right now, I'm going to start. When you take a look at what we have here, the list, I'm going to start with lasso. Please pay attention. Lasso, lasso will shrink. It's a regularization technique, using L1 penalty, right? To shrink. It's going to shrink the coefficient of unimportant variable to zero, right? Lasso perform variable selection. Lasso will remove, multicollinearity, but we only remove, because Lasso will remove multicollinearity because Lasso will remove what I call redundant predator. But the issue I have with Lasso? The issue I have with Lasso, there are situations where all variables, even though we know there is multicollinearity, but all variables in the model are informative to the response. None of them should be dropped. We can have that situation. For instance, if you are looking at what we call lung disease, if smoking and a particular variable is correlating, they have to be in the model. They shouldn't be dropped because they are all connected to the response. Even though they are causing problem, they have to be in the model. But lasso, we eliminate them because the lasso, we shrink them. We shrink the regression coefficient to zero. When it shrink the regression coefficient to zero, it's actually going to eliminate some variables. And that is why when the only reason why you should use lasso is when you actually want to sparse your model for model sparsity. Maybe you don't want so many predator variables. That is the only reason why you should use lasso. Now, The next on the ladder is principal component regression. The principal component regression will eliminate multicollinearity. How? Because it's using a principal component as a predictor. The principal component generated, they will be uncorrelated. And the moment they are uncorrelated, they are actually going to eliminate multicollinearity, but there's an issue of interpretation. Are you enjoying the story? For the principal component regression, it will eliminate a multicollinearity. Okay, everything nice, except that there will be issue of interpretation. Why issue of interpretation? Because the principal component generated that you use as a predictor is still a linear combination of the original predictors. That will be interpretation issue. And not only that, apart from having interpretation issue, the principal component generated, okay, was based on variance maximization of the predictors only. And the next on the line, okay, is a partial least square regression. Let me tell you this. When you want to talk about in terms of effectiveness, ridge regression is the most effective. I'm going to tell you the reason. Ridge regression is the most effective, followed by partial least square regression, followed by principal component regression, followed by lasso. Now, let me start. Why is the ridge the most effective in dealing with multicollinearity? Is because the ridge will not eliminate any predictor. The only thing ridge is going to do is to shrink their regression coefficient towards zero, but not exactly zero. All of the predictor, they're still going to be in the model. When predictors are in the model, when all predators are in the model, in a situation where all predators are informative, even though there's a problem of multicollinearity, using ridge will actually reduce the effect of multicollinearity. So ridge regression has more predictive power compared to lasso, compared to other, regression type technique that we use to address multicollinearity. So ridge will retain information. Ridge will not eliminate any variable. Situation where all predictor variables are informative. Informative means where they are all connected to the response and we are never going to drop. We know where it is not recommended to drop any variable. The ridge regression is the most appropriate in dealing with multicollinearity. So I rated ridge as number 1, followed by the partial least square regression. Partial least square regression is very effective. With a partial least square, the only issue that we're actually going to have with a partial least square regression, let me just tell you this. Both principal component regression and partial least square regression, they have interpretation issue, except that the partial least square regression will outperform the principal component regression because the principal component constructed using the partial least square regression put into consideration maximizing covariance between predictor and the response. Statistical world is so beautiful because we have alternative models that can be used for a given situation. And before we can settle for a model, I think it is better we explore different kind of models to be able to know which one worked better for which one worked best for this situation at hand. But let me tell you this. If you have data set, and you really want to know which one is better, somebody can conduct a research on comparing all this model. What are you going to compare in all this model? Compare their mean-square error for prediction or the root mean-square error for prediction at the end of the day. Of course, the one with the lowest mean-square error for prediction should be the best model. But I'm just trying to tell you, on average, a model that could perform. And let me also tell you this. The reason why we prefer a model may not just be as a result of maybe it has a lowest mean-square error. I told you something about range. Situation where all the variables mentioned, all the predictor variable mentioned, they are relevant to the predictor. I mean, to the response. Even though there's a problem of multi-collinearity, they need to be in the model. None of them should be dropped. Then reach is a very good idea. It's a very good approach. You know, I told you the other time, removing a predictor from a model. Let me tell you this. If a predictor is significant, do you know at times if I remove a predictor that is significant in the model, the predictive power can go up. Why do you need a predictor that is significant in your model? Oh, you need a predictor that is significant in your model because you are seeking an explanatory goal. When you are seeking an explanatory goal where you are looking at the effect of a predictor on a response, then those predictors in your model need to be statistically significant. But if I'm seeking predictive goal and they need to be in my model, whether they are significant or not, I need them in my model. Does that make sense to everyone? Okay, so we have compared all these models. Okay, I said, starting from the all subset selection, stepwise regression, lasso, ridge, principal component regression, and partial least square regression, they are all alternative way of, dealing with multicollinearity. Okay, so before I go, next week is very crucial. Next week is a week of revision. For this class, it's a week of revision, a week where we go through a practice questions. Initially, the midterm was scheduled for Friday next week, but it shifted to the following Monday because we have some students also, uh, you know, they are also in another class, and that immediately after that class, we have this class, and that will be too much for them. Check the calendar on Canvas. I've already changed. So I need you to be here on Monday, and I need you to be here on Wednesday. I need you to be here next week because next week, I think I'm ready now, to post practice questions. What we're gonna do next week is to walk you through practice questions, to tell you expectation, the way I want a question to be answered in exam. And for those of you who have attended my my lecture before, of course, my practice questions closely match, the real exam. Therefore, I need you to be around. Also going to be recorded. Is there any question for me before I go today? Okay, be sure you stay safe. Have a lovely weekend. Bye for now, everyone. Second. Let me just